Okay, so the next topic I want to touch on is momentum in dealing with momentum in collisions. So really I just want to talk about our two main types of collisions that we look at, and then a little bit to do with impulse that I think it's possible you'll see on the exam. So we'll just work through two collision problems and then talk about impulse and graphs. So let's say we have two little boxes that are moving towards each other, right? Let's say this box has a mass of 2 kilograms, this block has a mass of 1 kilogram. They're moving towards each other. Let's say that this is block 1, this is block 2, I guess. So let's say that block 1 has an initial velocity, block 1 has an initial velocity, right, of 2 meters per second, and block 2 has an initial velocity of 4 meters per second. But to the left, right, direction is important here. So it's actually -4 if we're calling right positive, which is our go-to. So this is actually negative. The signs are very important here because momentum is a vector quantity because it includes velocity, right? And velocity is a vector quantity. Okay, so two types of collisions mainly that we deal with. Technically, there's like perfectly, perfectly elastic or inelastic and all that. But really, we're just concerned with the basics of elastic versus inelastic and how you approach those problems. So, but the problem will tell you which one it is, generally speaking, unless they give you final velocities and ask you for it. But generally, it'll say, okay, this is an elastic collision, this is an inelastic collision. What's going on? So the first thing we're going to do is we're going to say that this is an elastic collision. The problem tells you, okay, this is elastic. Now, elastic means that they bounce off of each other, right? And you go from there. So let's say when they're bouncing off, right, they both move off with a different velocity, right? So if you have only these two, you can't find two missing velocities. That's not enough information. So it will always give you, if it's an elastic collision, it'll always give you one of the block's final velocities. Either it stops moving or it changes direction or it keeps going. It's going to give you a final velocity of one block or the other block. So let's say that block 1 has a final velocity of let's call it -1 meters per second, I guess. I hope that doesn't break my numbers. Let's call it -3 just to be safe, actually. -3 meters per second. All right. So block 1's final velocity is -3 meters per second after the collision, right? So it's going back this way at a velocity of -3 meters per second. And we're looking for the final velocity of block 2. All right. So the basics of conservation of momentum are very similar to any other conservation we've talked about, especially conservation of energy. Basically, the idea that the momentum is the letter P, right? It's actually a rho, but it's a P. Who cares? Greek alphabet nonsense. So the initial momentum is equal to the final momentum of the whole system. The system including both blocks, the momentum is constant. It never changes unless there's an outside force acting on it, right? But these are just hitting each other, so that's an internal force. So the initial is equal to the final. And then we, same thing that we do with energy is you're just calculating the two types, right? So initially we have momentum of block 1 plus the momentum of block 2, right? And momentum, the way you calculate momentum, it's mass times velocity. It's mass in motion. So the this would be the initial momentum of block 1, right? Plus the initial momentum of block 2. We always add them together because your signs are taken care of in your velocity, right? The velocity is where the sign comes from, not the equation. So momentum, you're always adding the total momentum. It's the sum of momentums, but the signs are taken care of in the velocity. So that's our initial momentum, right? Block 1 and block 2. And then our final momentum, same thing, except it's the final velocities. M2v2. Great. So we have masses, we have all but one velocity, so we can plug in and solve for our missing one, right? So our mass of block 1 is 2 kilograms, velocity of 1 is 2 meters per second, 1 kilogram, 4 meters per second, 2 kilograms. Or sorry, negative 4 meters per second, right? I would have screwed up there. Final velocity is negative 3 meters per second plus 1 kilogram times our final velocity of block 2, which is what we're looking for, right? V2 is what? We should have calculated things before, right? 2 times 2 minus 4, oh, that's 0. So negative 6 V2 should be 6, right? Easy peasy. Because these will cancel each other out, that's 4, minus 4, so we have 0 total momentum here. And then we have negative 6, so we need plus 6 here, so V2 is 6 meters per second. Who needs calculators? Great. So they bounce off each other and go opposite directions. One with negative 3 meters per second to the left, and 2 with 6 meters per second to the right. So yeah, easy setup here, right? Just an easy just set up and plug in and solve. A few details I want you to notice is that so block 1 went from it's 2 kilograms. It went from 2 meters per second to negative 3 meters per second, right? So it went from positive 2 to negative 3. That's a velocity change of 5, right? 5 meters per second's difference between 2 and a negative 3. And if we're calculating its change in momentum would be its mass times its change in velocity, right? That makes sense. Mass isn't changing, but velocity is. So our change in momentum here would be it changes by 5, right? Technically negative 5 if you're tracking, but that's not all that important in what I'm going to show you. So we have a change of momentum of 10 kilograms times meters per second. No pretty units for momentum, right? And our change in momentum for block 2, m delta v, it's 1 kilogram, and it goes from negative 4 to positive 6, right? Negative 4 to positive 6, that's a change of 10 meters per second. So 1 times 10 is 10 kilograms times meters per second. So I wanted you to remember that in a collision like this, both of the objects experience the same change in momentum, right? The same change in momentum. Remember that impulse is just a change in momentum. It's just another word for change in momentum. And impulse can be calculated by force times time, right? The force you apply to something times the time it takes to apply, or the time you apply that force. Remember I told the story about the friendly butterfly and the battleship and all that? But yeah, so these blocks collide. They apply a force on each other over a certain amount of time. That's the impulse, right? And when they hit each other, right, they're pushing, they're applying equal and opposite forces on one another, right, and they're in contact for the same amount of time, so they apply the same impulse to one another, right? So we should see the same change in momentum, and we do. The forces are obviously in opposite directions, which makes it the sign change, but yeah, they both, in a collision, both objects experience the same impulse, the same change in momentum, just in opposite directions. So I wanted to remind you of that. All right, so that's an elastic collision. Now we'll say inelastic collision, where they stick together, right? Inelastic is where they stick together. That's your cue. If they don't say inelastic, that's your cue for it being an inelastic collision, is them saying the objects stick together. So they stick together and they move off as one. If they're moving off as one object, obviously they have the same final velocity, right? They stick together and move off together, so they have the same final velocity, some sort of same final velocity, and that's in that case, that's what we're looking for here, right? Because we're given these two pieces of information. So setup goes the same. Our initial momentum should equal our final momentum because there are no outside forces acting on this. So the plug-in is the same. Our initial momentum for block 1 plus our initial momentum for block 2 is equal to our final momentum of the system. So there's two ways you can do this. You can either treat the momentums of the blocks separately and say that they have the same velocity, like this. That's supposed to be an M. I say M and then I write V. M1V plus M2V, right? same velocity here, but the different masses are moving at the same velocity. That's one way you could set it up. Or the other way is treating it as if it were one large object moving off as one, and the one large object, its mass would be the sum of both of the masses, right? Times the final velocity. So our big large object has the mass of m1 plus m2 times velocity, and that's the same thing. You can see how those are equal via the distributive property, right? You can factor out a v, and that's how you get this. So either setup is valid, whichever one makes more sense to you, right? Either the one big object or both of the small objects moving at the same speed. But yeah, either way, setup is the same. I'm gonna use this because it's ever so slightly less writing, right? I write one less v. Although I guess I write the parentheses, so maybe it's about the same. Basically, we have m1, we have all the initial information. We're just looking for final velocity, and we can solve for that because it's their only missing variable. So just plug in once again, 2 meters per second plus 1 kilogram times -4 meters per second is equal to 2 kilograms plus 1 kilogram times our final velocity. Well, this is 0 again, so I broke the problem. I did a bad. So let's change that velocity real quick. Let's say that this one has an initial velocity of 5 meters per second. I changed this because we would get 0. They'd come to a stop, which is bad. That's not what we want. We want a number, because that wouldn't make very much sense for us. All right. So now we have 4 times, or minus 5 here. That's a -1 divided, and then we have a 3 over on the side, so we divide by the 3, right? So it's 1/3 if you're solving for it. 1/3 of a meter per second. Except it's -1/3, right? Because this would be a -1. So our final velocity is -1/3 meters per second, -0.33333, repeating, meters per second. So it's moving to the left here. That makes sense because our block 2 has more momentum than block 1 does, right? 2 times 2 is 4, 1 times 5 is 5. So block 2 has more momentum, meaning it will overpower the other block. But if you worked out the math here again, you'd see that again the blocks have the same change in momentum for the same reasons that I said before, right? They're in contact with each other for the same amount of time, and they apply equal and opposite forces. So that math would be the same as well. The impulse experienced by both objects is the same in a collision. All right, so those are our 2 collision types. Now I wanted to talk a little bit more about impulse, because I think that it's possible you'll see something like this next setup on your test. So impulse, they really like to give you impulse information in a graph, right? So it would be a force, you'll see it as a force versus time graph. Force versus time graph. In mine, I'll make a little, just a regular linear graph, and say that our maximum force here is 10 newtons, and it happens over the course of 2 seconds, I guess. All right, so it'll give you a graph, and it might just be asking you to find impulse. It might be asking you to find a change in momentum. Well, it is a change in momentum, same thing. So it might be asking you to find initial or final information. I'm going to have it, let's say that the problem says something like there is an object sitting, or it's in motion or something, you don't know, and this impulse in the graph is applied on it. And the problem says that it has a final momentum after the impulse is applied of, say, our final momentum of our object is 50 kilograms times meters per second, right? And it might be asking you, what is the initial momentum? So how do we figure that out? Well, remember, impulse is a capital J for whatever reason. Impulse is equal to, it's the same thing as change in momentum, right? It's the same thing as delta P. Or you can also calculate it by force times time, right? we're given a graph. Your go-to information for a graph is either pulling a value off the graph, taking the slope of the graph, or taking the area under the graph, right? And in this case, slope would be dividing, right? It's rise over run, so it would be force divided by time. That's not what we're looking for. We're looking for area under the curve, right? So area would be 1/2 base times height, our base being in time, our height being in force. But basically, you're multiplying the axes together, which is what you're doing here, right? Force times time. So we're looking for the area under this curve because we're multiplying these values together, right? Pretty straightforward. So yeah, our impulse is equal to the area of this triangle here. So 1/2 base times height, our base is 2 seconds, our height is 10 newtons, and impulse is, that's just a 1, just 10 newtons. Right, so that's our impulse, newtons times seconds. Yeah, impulse is measured in newtons times seconds traditionally, force is in newtons, time is in seconds, that checks out. Great. So impulse is the same thing as change in momentum, right? So our change in momentum is also equal to 10. Momentum is measured in kilograms times meters per second. These units are actually the same thing. You can reduce this into this or vice versa. They're interchangeable, they're equal to each other, so that should clue you in. It's just the units are just emblematic of how you calculate it, so don't let that confuse you. They're the same thing. So our change in momentum is 10 kilograms times meters per second. Now, obviously, so that's an increase, it's positive value, right? We have a force in the same direction as our momentum, it's a positive increase. I can easily say, oh, hey, the final is 50, we increased by 10, so our initial was 40, right? I feel like that logic follows. But I just want to write out the math, I guess, so that you can see how this actually looks in terms of physically calculating it. So how do we calculate change in momentum? Well, a change is final minus initial, right? So final minus initial is how we would calculate it. Our change is 10 kilograms times meters per second. Our final is 50 kilograms times meters per second minus our initial, right? So subtract over the initial, subtract by 10. Our initial momentum is 40 kilograms times meters per second, just like I said. Great. So that's how the graphs work. If you see a force times time graph or a force by time graph, that's usually your clue that it's an impulse problem, and you're going to have to find the area under the curve, because the area is how we do force times time, right? Area is force times time. Yeah, so that's impulse problems. Pretty straightforward. Impulse is just a change in momentum. Very last thing I wanted to mention at the end here is just that, because I forgot to mention it with the collisions earlier. If you recall, I did this proof where I proved it like 3 ways, that in a collision, there's this obsession with how the center of mass of the system is moving, right? Draw a picture so that you can see what I'm talking about. They're concerned about how the center of mass of a system is moving before and after the collision, right? So if you've got 2 boxes moving towards each other, the center of mass is like, say, here, and after the collision, they might ask you about center of mass motion or whatever. And my big reminder on that is just that if there are no external forces acting on the system, that the center of mass is moving the same way before the collision as it is after the collision, right? So in our basic collision setups, there are only internal forces, meaning that center of mass motion stays the same throughout before and after the collision. I'm not confident whether they'll throw you one of those in an FRQ. If it's like a momentum heavy FRQ, they might. It's just a remember thing, probably, is all that you need to do, that in a collision, if there are no external forces, center of mass motion stays the same. Yeah, but other than that, that's all that I want to touch on for momentum. So thanks for watching. Good luck on the practice problems. Bye.